a pleasure to be here and have a chance to talk to you about some of the work that we've been doing in my lab over the last 3, 4, 5 years or so. And it's pretty heavy on the engineering component, but we're very much interested in the interface to biology as well, as you'll see as I make my way through the slides here. And it's an area of technology, I guess, that we're referring to as bio-integrated electronics, in the sense that the electronics is intimately in contact and able to communicate electrically, chemically, thermally with the tissue of a living system. And so I'll start by giving a motivation of what this field means to us. You know, it's a little bit of a perspective on how it's fitting with other future directions in electronics and aligned with those efforts, actually, complementary to them. And then I'll switch over a little bit and talk about some materials and mechanics aspects of how to make electronics into a form that can accomplish this level of biointegration. And then conclude with some functional system level devices that we've built that appear to have some clinical utility for advanced surgical procedures. So if you think about electronics, and just as a side note, I mean, a lot of the slides that I'll go through here are pretty basic. I mean, if you're interested in deeper level of detail, just let me know. This is very much high level, just to give you a sense of what we're doing and what the trajectory is. So this slide just provides kind of a primitive view of where electronics has been in the past, where it is now, and where it might be going in the future. So if you think about, half a decade ago or 30 years ago, this is the kind of computing systems that one would typically encounter. Large boxes that would sit on your desk or fill entire rooms, and really by virtue of Moore's law scaling, transistors getting smaller and smaller, and the ability to pack more and more of them into smaller and smaller areas have enabled this kind of functionality to be reproduced in devices that, instead of having primarily industrial utility, are now valuable at the personal level because of the small size and the advanced functionality. And so if you think about where is electronics then going in the future, one dominant trend would obviously be to simply continue this kind of Moore's law scaling to enable even smaller and smaller devices, even more and more powerful, power-efficient computing systems. And that's certainly an interesting direction to go, and that will continue for some decades or so. The other area is a little bit less familiar, would be to focus on advanced display systems or components of these computing devices to make them larger in area, or maybe mechanically flexible, or offering other kinds of functionality. And that is a direction in macroelectronics that have different scaling metrics in terms of measuring progress, but is nevertheless an existing and continuing direction for electronics. The third thing that you might think about, I think about others as well, would be to move these things from the desktop to the individual, and ultimately integrate them in an intimate way, either on the surface of the body through a skin interface, or implanted into the body itself. And so these kinds of notions have been kicking around for 30, 40 years or so. So it's not a new field by any means, but I think there are new opportunities that emerge from new developments in form factors, shapes, properties, mechanical characteristics of electronics that allow one to come back to this kind of vision and maybe do some useful things. So if you think about existing bio-integrated devices, there are lots of examples. Again, this is an area that people have been thinking about for a long time. The ones that are in widespread commercial use are kind of summarized here. I'm not going to step through all of these examples, but just highlight a few. There are deep brain simulators that are used to deal with Parkinson's disease that involve electrodes penetrating down into the depth of the brain. Those are in widespread use. Cochlear implants to restore hearing to the hearing impaired. Other things, pacemakers, other kinds of devices, all of which offer some active level functionality. There are other kinds of devices that provide a more passive role, such as contact lenses. And if you look then at the range of stuff that's available, all of the active devices have this kind of construction, more or less. That is to say, it consists of two parts. One is the active electronics piece, which is typically in a rigid box. And then the interface to the biology happens through a small number of individual electrodes that penetrate into the tissue to form the interface. And that's fine for certain of these kinds of applications, but you can imagine that that kind of design approach is highly limited in terms of what you might be able to do, and also in terms of the long-term viability and biocompatibility of a system like this. On the other hand, some of the passive devices maybe embody a much more appealing design, the contact lens being an example of that, where the device itself takes on the shape, the form, the mechanical properties of the tissue that it's integrated with. And so contact lens is curved to match the curvature of the eye, and it's soft and water permeable to provide a much more robust and attractive type of interface to the tissue. And so, you know, the question that we've been exploring is to figure out whether it's possible to embed, you know, full active functionality that's available in something like a brain stimulator. It may be more advanced than this, but in a mode that integrates with the body much more like a contact lens might do. And so there are lots of potential contexts for utility of that kind of envisioned system. Probably the most obvious one would be to form an interface to the brain, either to provide kind of advanced diagnostic or therapeutic function for a surgical procedure, or ultimately to provide an interface to a machine or prosthetic or something that sort. And so if you think about the brain, I mean, it's an electrical device, and if you wanted to interface to it, you know, a man-made piece of electronics, you might ideally want to bring to bear on that problem the full integrated power of silicon Cmos technology. But that kind of technology only exists in this kind of form. And so you can imagine that establishing an interface between these two things would be challenging because the shapes are totally different. And the mechanical properties are too. So the silicon has a modulus of about 100 gigapascals. The tissue typically will have a modulus between 1 and 10 kilopascals. So many orders of magnitude separation, and then the obvious challenge in geometry. And so what do people do? Well, this is the current state-of-the-art technology that people use to interface electronics to the brain. It's been around for about 15 years. It's known as the Utah arrays, and I don't mean to denigrate it at all because it's been a spectacularly valuable type of tool for doing all kinds of research in brain function, but the mode of operation has certain kind of obvious limitations here. So the system consists of an array of micro-machined sharp pins of silicon that terminate at their tips in an exposed electrode that then interfaces to the brain tissue. On the other side of those pins is a flat platform on which you can mount a chip that you might dice out of a larger wafer. So you integrate those two things, pins and chips, and then use an air hammer to plunge it into the tissue of the brain. The pins penetrate and sort of accommodate the curvature, the mismatch in shape, the curved surface, reticulated curved surface of the brain, and the flat silicon chip. And that works okay for typically a few months, but you can imagine that's not a viable system in a long-term sense for two reasons. One is that there's a lot of damage to the tissue upon insertion, and then even after that, these tips tend to rattle around in the brain as the animal or the patient moves around. Because that brain actually moves in the head to some significant, in the skull to some significant amount, and then the modulus mismatch between these sharp high modulus pins and the tissue causes continued irritation that degrades the signal level here and also continues to damage the tissue. And so the vision then is pretty simple, which would be to try to form electronics that have you know, performance characteristics that we all know and love, you know, from silicon wafer-based CMOS, but in a form that's soft and shape conformal to the tissue to enable, you know, an intimate type of biointegration and long-term viability in the sense of being biocompatible. Okay, so that's the idea. That would be an example of what you might think of it as an indwelling biointegrated device. It's mounted on internal tissues, and I'll come back and describe some specific examples of brain-integrated electronics a little bit later in the talk. Other areas that we've worked on is in cardiac monitoring. The other point of integration, though, you could conceive of is on the surface of the skin. Would be a lot of interesting things that one could do there as well. The challenges are sort of similar to the ones I just described in the sense that the skin has tissue-like modulus that's much, much lower than silicon. It's also curved and sort of stretchy at some level. And so if you want to integrate electronics on the skin, you need to match all of those kind of properties in order to do it in a viable way. The other problem and challenge with the skin is it's constantly reconstructing. So it involves several different layers here. Cells in this base layer differentiate and migrate to the surface of the skin over time, where they eventually die and form this hard horny layer, sort of protective coating on the skin known as the stratum corneum. And this happens on a time scale of a couple weeks. And so if you want your electronics to sit on the skin, you need to worry about the modulus and the shape and whatnot. You also have to worry about this cellular escalator, essentially, and what you're going to do with the need to exfoliate these dead cells. And that creates a whole other set of challenges that we haven't directly addressed. We just highlight that as maybe an area of future opportunity with electronics that can kind of accommodate that kind of exfoliation and evolution of the underlying tissue. So in this area, as in the brain interface electronics area, there's been a lot of work over the years, and there are a lot of current research efforts. Last year we did a study for DARPA to sort of map out what the landscape of current work looks like. And these are representative of two classes of devices that we could sort of bin all of the existing efforts into in very rough sense. One is this sort of deep brain stimulator type of geometry where you have a brick of electronics, in this case, mounted on the body through straps, and then small numbers of electrodes interface with the skin. That's one direction that people are pursuing with its obvious limitations. The other is a little bit newer, but also a little bit primitive, which is to just glue chips onto tapes and then tape them against the skin. So the point I think here is that there are existing technologies. They have advantages and disadvantages. Maybe a new way of thinking about things could push the field forward. Okay. So if you think about then those kind of indwelling and non-dwelling electronic systems, the challenges really are in the interface. How do you do it? Long-term viability, but you still need optical, electronic, chemical access. How do you make things stick without irritation? Mechanics and shape are important here because they affect these two things. They also determine sort of wearability. And then there's a whole host of sort of DARPA-related metrics that would be important, for ultimate commercialization of these kinds of systems. So, cost, power, weight, size, this kind of thing. So what we've been trying to do is to realize a vision that looks like this in terms of electronics, which is to make electronics themselves skin or tissue-like as much as possible. And so what does that mean? That means making the electronics ultra-thin. That should be 5 microns. So much thinner than the skin, for example, much thinner than the surface layers on many internal tissues. Ultra light to minimize the mass loading, ultra low in modulus to minimize the mechanics loading. So that means circuits with moduli in the 5 kilopascal range or smaller. If you could go smaller, that'd be even better. This is sort of the target that we put up for ourselves. Shape conformal and perhaps air and water permeable and waterproof. It has to operate when completely immersed in biofluids. So the vision then becomes one of kind of an electronic temporary tattoo. So you're probably familiar with these kids' tattoos. They're very thin. They have many of these kinds of characteristics. And the interesting thing about them is once they go on, then the user loses all consciousness of the device actually being there in the sense that it moves freely with the underlying tissue. And so the question is, can you make silicon electronics into that form and design it to provide some kind of useful function? And that's what we've tried to do. So if you think about that as an outcome, it's useful to consider the backdrop of a sort of researchy, but technology that's beginning to near commercialization, and that is organic electronics and flexible devices. So this is an area that we've been interested in for a long time. This is some early work from a team effort that we had when I was back at Bell Labs. We teamed up with E-Ink, which is a company now that provides the ink material for the Kindle, but this was the early days. This was 2000, 1999 or so. But then one interesting thing about that kind of material is it's thin and flexible, has the look and feel of a sheet of paper. And when you display, you need more than that, though. You need also a piece of electronics to turn on and off the pixels in that material to bring up images or text. And so we, at that time, were interested in organic-based electronic systems, so polymers or small molecules that could provide a semiconducting function in transistors that you can then form a sheet of plastic. And in this case, we built an array of such thin film transistors. When integrated with E-Ink's electronic ink, you can make sort of a paper-like display. At that time, we thought that that might be an interesting type of consumer electronic device. And a lot of companies since then have pushed it forward and just developed the engineering sophistication to point out that you can really envision things like electronic newspapers that have the look and feel of paper, and that's moving forward. Now, this is not, in my opinion, a viable technology foundation for the kinds of biointegrated electronic systems I described before, for several reasons. One is that the performance that's available from these classes of materials is pretty lousy. It turns out to be good enough for that kind of display. If you want to do any kind of high-frequency electronics, it's not going to get you there. The other, and sort of reliability, robustness questions still remain, even though things are moving towards commercialization. The other limitation here is that in this particular form, the electronics are in a sheet of plastic, and so that's bendable. But in order to integrate with biology, you need something that can not only bend, but also stretch and flex and twist in ways that enable this kind of modulus matching. And this ain't it. So this is relatively still high modulus. I mean, the plastic is a few gigapascals, so still many orders of magnitude higher than your tissue. It's flexible. That's great for a flexible display, but not good for biointegrated electronics, which is our present focus. So how do you do this then? So you like to do it in silicon. It's established material. People know how to build high-quality devices and circuits out of it. But you think of silicon typically in the form of a semiconductor wafer, which is certainly not bendable, low modulus, and not able to wrap curved surfaces. So I'll just describe two very simple ideas that allow you to bypass that apparent limitation to build the kinds of systems that I just described. And the first idea is based on elementary bending mechanics, which dictates that for a given bend radius, the maximum strain in the material decreases linearly as you decrease the thickness. That's it. So 2x4 is not flexible. The sheet of paper is the same material essentially, but just by virtue of the fact that the paper is thin, it's bendable. So the same elementary mechanics applies to silicon. So if you can take a bulk wafer, which might be 0.5 millimeter thick, and slice it very, very thin, then the silicon becomes flexible. And so there are ways to do that. You can take a commodity 111 silicon wafer. If you do a two-step etching process, which involves a vertical trench etch, followed by top surface sidewall passivation and an anisotropic undercut etch with wet etchant like KOH, then you can slice off of the near surface region of the wafer very thin ribbons, wires, platelets, membranes of semiconductor grade silicon. And that's what's being shown here. So this is a cross-sectional SEM view after this undercut etching is proceeded for a little while, but not completely undercut the ribbon, just to illustrate what's going on here. Typically, in a real process, we completely undercut. And in that kind of thickness range, 150 nanometers or so in this particular case, the silicon becomes quite floppy and bendable, just due to that elementary bending mechanics that I mentioned before. So if you take that form of silicon, there are different ways to manipulate it and integrate it onto a thin, flexible substrate to make a flexible but still high-performance form of electronics as an alternative to this organic approach that we worked on and others are still working on over the years. So this is an example of an extreme implementation of that particular idea in the form of simple silicon Cmos circuit elements. So what this consists of are very thin ribbons of P and N-type silicon, and then other components, layers of material to form simple logic gates. So these are Cmos inverters, an array of them. And they're built actually on a very, very thin sheet of plastic. This is polyimide. Just to illustrate how bendable you can make a silicon circuit. So in this case, making the silicon thin and also making the substrate thin makes this thing very bendable by virtue of the mechanics I just described. But you can actually do even a little bit better than that if you think a little bit more carefully about the mechanics. And so this also exploits not only ultra-thin plastic substrate, but a design that places what's called the neutral mechanical plane coincident with the most brittle material in these circuits, which happens to be the silicon. So the neutral mechanical plane is also a really simple idea. So if you have a sheet of plastic, let's say, just a uniform sheet of plastic, and you bend it like this, the top surface is in tension, the bottom surface is in compression, and the geometric midpoint sees zero strength. That's known as the neutral plane. And such a plane exists not only in a uniform sheet of material like I just described, but even in a multi-layer stack like this. It doesn't happen to lie at the geometric midpoint, but you can go off and calculate where it is. And in this case, we chose the thickness of the plastic substrate to put that neutral mechanical plane aligned with the silicon. So the neutral plane is indicated by the red dashed line here. And so that further enhances the flexibility of these devices to the point that you can, for example, wrap these circuits around the sharp edge of a microscope cover slip. So that radius of curvature is between 25 and 50 microns, for example. You can also wrap it around a capillary tube, fairly tight radius of curvature there. So I think the message here is that these simple ideas, you can make silicon circuits as flexible as you want them. I mean, down to a level that's almost foldable in some ways. But as I mentioned, in the context of that flexible display, flexible is not good enough. You need more than just flexibility if you want to do biointegration, because although you can wrap a cylinder or a cone, you can wrap a sharp edge, you can't even wrap a sphere, certainly can't do a body part or a complex curvilinear shape like the surface of the brain. So that brings me to the second simple idea, which is that if you make silicon thin and you also structure it into an accordion type geometry, then you can achieve sort of an end-to-end stretchability in silicon without inducing any significant strains in the material itself. And you can do that in a variety of ways. In this case, this is an image of that kind of wavy ultra-thin silicon bonded to an underlying rubber substrate. So the way this works, you actually stretch the rubber substrate out a little bit. Then you deliver to its surface these thin strips of silicon. It bonds through interface chemistry that you define explicitly. And then when you allow the rubber to snap back to its original dimension, it puts these ribbons into a state of compressive stress. And the way that the material responds to that compressive stress is through a nonlinear buckling instability that spontaneously yields this kind of wavy silicon. And so at a very intuitive level, the response of these wavy ribbons to strains that you apply, let's say, along this direction is very much compatible to your intuition of how an accordion works. So if you stretch this material in this direction, the amplitude goes down, the wavelength goes up in a way that avoids any kind of significant strains in the silicon. And the reverse thing happens if you compress it. The amplitudes go up, the wavelengths go down. Okay, so that's the intuition. Of course, the detailed mechanics are a lot more complicated than that. And because mechanics is playing a central role in the design layouts in these cases, we work with theoretical mechanicians to be sure that we understand all fine details so we can optimize our circuits using this kind of idea. So that's the idea in its simplest form. That's not a circuit technology, obviously. It's just a pieces of silicon on a rubber substrate. But you can combine those two things. So these ultra-thin plastic-supported silicon circuits with this neutral mechanical plane design combined with this idea of buckling and rubber substrates to achieve full integrated circuits that are stretchable. And this is an example of one of those kinds of wavy circuits. Again, this is one of these Cmos logic gates where we have a P-channel MOSFET here, an N-channel MOSFET over here, and then we have the wiring that connects them up in the appropriate way to make this inverter. And what you're seeing here is this circuit is supported on a thin sheet of polyimide, like I showed you before, and then the underlying substrate is a silicone elastomer. And this is what it looks like after that buckling instability is invoked as a result of relaxing the pre-strain that's applied during the bonding step. So, again, finite element modeling and mechanics is central here. So this is an example of full 3D modeling of this particular structure. Now, what you see is the pattern of waves is actually a lot more complicated than in the case of just these uniform strips of silicon. But that's easy to understand because this circuit is both heterogeneous in materials. Silicon is here, for example, it's not over here, and also in thickness. So the local bending rigidity of the circuit varies depending on where you are in the circuit. So in this particular case, bending rigidity is lowest at these interconnect lines, highest here. So the waves tend to localize in those regions that are more easily bent than the locations of the silicon transistors. So this is just a short movie to show that buckling process, looking at top-down view through an optical microscope. There are the transistors. You can see this buckling set in as a biaxial pre-strains relax in the substrate. So that's the physics at the level of its single inverter, but you can apply that idea chip scale. So here's a little bit more advanced system consisting of 10, these are 10 Cmos ring oscillators, just 3-stage ring oscillators. Here are inverters down here and individual transistors up here. So this is supported on rubber substrate. You can see the wrinkles and the wavy nature of this ultra-thin circuit. The photographer who took this is actually illuminating the circuit to highlight that kind of out-of-plane deformation due to the illumination angle. So what we're seeing here is the troughs appear black and the raised peaks in these wave structures appear bright, just due to the way the light is reflecting. So it makes it look as though this thing has been deformed at a level that's a little bit more extreme than it actually is. So for these waves, the wavelength is maybe a few hundred microns, and the wave amplitude is a few microns. But that kind of mild wavy shape is enough that allows you to take this circuit and then stretch it back and forth this way or that way, or whatever way you want, without changing significantly the properties of the devices, or certainly not fracturing the silicon. To some limit, I'll come back to that in a second. Yeah.
Do you have wavy pattern in both?
Yeah, so you can see sort of wave structures here, and then also wave structures there, and they're bottom of the line.
To see how good is the react. Do you verify how is it fracture or after a few cycles of this kind of buckling process?
Yeah, so that's a good question. So we have mechanical fatigue testing setups that allow us to cycle these devices back and forth. So we'll, in an aggressive test, we'll run up to maybe 100,000 stretching cycles up to some predefined strain level. We also do bending fatigue as well. So I think at an academic level, that's pretty good. For a real commercial product, you may want to go even a little bit beyond that. But these systems are designed up front with full quantitative modeling of the mechanics, such that we know what the peak strains and stresses are at different locations in the devices and the circuits. And so they're designed specifically to accommodate a certain range of stretchability. And then we verify that through this fatigue analysis. Somebody else have a question?
Do you have blockage?
So you can. So there depends on the thickness of the substrate. There is some residual stress in the system. So the top surface is a little more highly stressed than the bottom surface because it's mechanically loaded by the circuit. So if the thickness of the bottom substrate is sufficiently large, then you can get an overall bowing effect rather than local wavy shapes. And so I'll show you in a couple of slides a more advanced design that we more routinely use these days that avoids that kind of problem. It was very good point. Yeah.
What's the purpose of using that polyimide substrate? Is it for having more flexibility in the structure?
It just provides, so actually
Can you repeat the question?
Yeah, so the question is why use the polyimide? Why not just the silicone, I guess is the question. So the silicone is a low modulus material. It's a modulus about 1 megapascal. It's slightly gas permeable. It's also permeable to certain classes of solvents that you might want to use in a semiconductor fabrication sequence. And so it's useful to separate the elastomer from everything associated with fabrication of the circuit. It also has a very large CTE. So we use the polyimide as a support for fabricating the circuits, and then use that in a final step for integration with the silicon. So polyimide is just a much easier material to work with during circuit fab.
Does it have good adhesion with the silicon?
Yeah, so polyimide is used in packaging applications currently in the silicon industry, and in some cases it's used as an interlayer dielectric. So in that case and others, we're usually trying to select polymer materials that have already had some validated range of applications in existing conventional silicon ICs. And so those kinds of problems have been worked out for us, and we try to just build on that and exploit it. Yeah. Any questions?
Is there any limitation about the circuit different way we say?
Yeah, I'll get to that. There are limitations. So this is a concept, but it's not magic, you know. So there are limitations. I'll come to that in just a couple slides. All right, any other questions or comments? Yeah.
How to control the fatigue loading about the stretchable silicon?
How to control
The fatigue loading.
So we control the fatigue by designing the layouts to avoid any stress concentrations at interfaces or in critical material elements. So it's really mechanics design that's done alongside of circuit design to create a layout that's robust to fatigue. That's one part of the answer. The other part of the answer is that monocrystalline silicon, in that sense, is good not only because it's attractive electronic properties, but it's also known to have very good fatigue resistance because there are no grain boundaries to migrate during cyclical stress loading. And that's already established from the MEMS community. And so, you know, we do our own fatigue testing, but I think there's ample reason to think that, you know, monocrystalline silicon is good not only for electronic properties, but also fatigue. Okay, so these circuits are not only stretchable, but they're soft, you know, at a mechanical level. And this was a nice image that people in our Beckman Institute took for us. We dropped off the circuit, and they came up with this nice posing, which I think is aesthetically appealing, but also kind of demonstrates the physics a little bit. So what this is one of these wavy circuits on rubber, and then into the center of this thing, the photographer plunged a glass pipette to induce some local deformation here. And what you can see is these wave structures move into form to accommodate this kind of local strain. So in this line back here, which is analogous to this line here, you can see that the wave structures are still present. In this particular case, though, the waves have sort of been pulled out as this line has extended in length to accommodate this local force. And so that kind of illustrates the physics. It also illustrates a limitation. So you can imagine if you continue to press this thing, this particular line is already flat. It doesn't have any geometrical ability to continue to stretch. And so it will fracture if pressed much beyond this particular level. So there's a finite range of stretchability in these systems that one can compute and then design around using approaches I'll describe in a second, or right now. So that's the idea. So there are two limitations here. One is range of stretchability. The other thing is that because this circuit is all interconnected together by that underlying sheet of polyimide, when this thing is pressed down, the silicon transistors see a bit of strain also. And the strain couples to mobility. So depending on how you're stretching or twisting or torquing this thing, the current outputs in individual devices could fluctuate up and down by maybe 20%, just due to that strain-induced change in the electronic properties. And depending on the circuit design, that may or may not be a problem. So you'd like to better strain isolate the active devices, those that are sensitive to strain, and you'd also like to expand the range of stretchability. So the particular range of stretching that a circuit like this can accommodate is maybe 20%. So that's maybe a factor of 10 or 20 larger than the intrinsic stretchability of the silicon, but it's not stretchable like a rubber band. Okay, so in some of these biointegrated applications, you'd want something that's more like latex, and this is not it. And so how can you bypass those limitations, but still retain silicon and some of the simpler ideas that allowed you to get to that point. And the answer is that you do two things. One is instead of the circuit existing in a uniform sheet, you etch it into the geometry of an interconnected mesh. So in this particular case, it's just a simple illustration of the idea. It's islands connected by straight bridges. So this is a thin sheet nanomembrane of silicon, and structured into this mesh, number one. And then number two is by controlling the surface chemistry of the underlying silicone rubber, you can induce selective bonding of the silicon only to these island regions. So if you do the bonding of a mesh like that on a piece of silicone that's pre-stretched, and then you relax it, what happens is that the interconnecting ribbons deform out of the plane to form these kind of arc-shaped structures that accommodate all of the relaxation of pre-strain in a way that strain isolates these islands. So the concept then is to use this kind of idea, implement a circuit in which your active devices are in the islands, and then these non-coplanar bridge structures support the interconnect. Okay? So this is an example just in silicon. You can see with this kind of, those two ideas, you can really accommodate very large strains with a completely linear, elastic response of the overall system. So these things can stretch 100, 200%, much more like rubber band. So those are the ideas just implemented in a sheet of silicon. As I mentioned, you can use those concepts and extensions of them to build silicon electronics. And here's an example of that. So this is an island, a silicon CMOS here. And then these are, in this case, non-coplanar serpentine ribbon cables, essentially, that are connecting these individual islands together to form an overall system that has some kind of functionality. Now, the concepts of neutral mechanical plane are implemented in this kind of ribbon. So it's actually a polymer metal polymer stack where the metal's at the midpoint to improve the flexibility of that line. So you can do full finite element modeling. This is what these interconnects look immediately after fabrication. It's about 20% pre-strain, and this is after stretching to 60% or so. So the strain at the locations of the silicon device is very, very small with these kinds of designs. Now, in a real system, you encapsulate the top of this thing with another low modulus elastomer so that these fragile interconnects don't come into mechanical contact with the environment, which would obviously be a problem. So that's stretchable circuits. If they're stretchable, then they are also deformable in a way that allows you to wrap complex curvilinear shapes and also integrate silicon ICs onto a variety of unusual substrates. So here's silicon on paper. You can bend it and fold it without affecting the operation of the circuit. Here is silicon ICs on the tip of a latex glove using the ideas I just showed you. And here's an example where we wrapped silicon electronics onto the dimpled surface of a golf ball. And I have no idea what that's useful for, but you can do that just to illustrate the concept. So you can do it with silicon. Nothing I've told you, though, is particular to silicon. So any kind of inorganic, brittle semiconductor material can be used in this way. And so you do not only electronics, but photovoltaics, LEDs, photodetectors, anything you want. Here's an example of microscale LEDs, red LEDs based on Allen gap quantum wells that we grow on an epitaxial layer of aluminum arsenide, which can be selectively etched in HF to release these very thin active layers from an underlying wafer substrate. So the release process is a little bit different than what I showed you for silicon, but the concept is essentially the same. So the process for building these thin LEDs involves laterally defining their geometries by vertically etching down through the active materials to expose the aluminum arsenide. Then we pattern little pieces of photoresist that anchor these devices to the underlying layer after they're completely undercut etched by immersion in HF. So these devices are in a diving board type geometry anchored at their endpoints by these photoresist anchors such that they don't lose their lithographically defined locations and simply wash off into the etching bath after eliminating this aluminum arsenide layer. So this is what the wafer looks like. And then we have soft rubber stamps that allow us to come in and pick off selected devices from the growth substrate and then deliver them down onto plastic or rubber for making functional systems. So here is an array of such kind of ultra-thin LEDs interconnected using these non-coplanar serpentine ribbon cables I showed you before in the context of silicon electronics. So each one of those islands is an active LED. And you can see the interconnects, the ability to probe them here. The whole thing is sitting on a piece of silicone rubber. So you can make arrays of LEDs, very thin, very low effective modules. You can put them on a thin membrane of rubber, for example. You blow them up like a balloon without affecting the operation. So the system is designed to accommodate very large stresses and strains, in this case sort of biaxial, but you can take these things and pull them down onto the sharp tip of a pencil without affecting the operation as well. You can put them on rubber bands, twist them up, do all sorts of things to these devices without altering the operating characteristics. You can also integrate them onto a latex glove. This is an optical proximity sensor consisting of an array of these micro LEDs and then a corresponding array of tiny photodetectors on a latex glove designed in a mode that can be operated underwater. And I'll come back to that in a second because all these biointegrated devices need to operate under salt water, and that tends to be a challenging requirement, especially when you need to maintain these attractive mechanical characteristics. And I'll mention something about that a little bit later, but here's an example of this. We have a funded program with a surgeon who'd like to put smart devices on a surgical glove. This is the first example of that. Okay, so that's the mechanics, the materials, some aspects of the technology. At this point, I'll shift gears and talk to you about actual systems that we've built in collaboration with surgeons and clinicians to satisfy some needs for advanced diagnostic devices in cardiac therapy and in electrocorticography for diagnosing epilepsy. But before I shift gears, are there any other questions about the ideas or the approaches or what's happening here? Okay, so let me start with cardiac electrophysiology. So the clinicians that we work with are at the medical school at the University of Pennsylvania. They're cardiologists, practicing cardiologists, and one of the problems that they deal with are cardiac arrhythmias, so irregular beating of the heart. And typically that is induced by locally aberrant tissue, parts of the cardiac muscle that are not firing in a predictable and regular way. And the clinical procedure to treat that form of arrhythmia involves two steps. One is mapping the electrical activity on the surface of the heart or in the interior of the heart as the heart is beating to identify the location and spatial extent of the aberrant tissue. And they do that by electrical mapping. And it's typically done with a single point electrode that is moved from place to place on the heart while electrical signals are measured. And in that kind of point-by-point fashion, you can map out where the aberrant tissue is. And then the second step in the process is to remove that tissue. You either resect it or you ablate it to eliminate it and thereby cure the arrhythmia. So these kind of procedures, there's some mortality rate, and the mortality rate is most strongly linked to the time of the procedure, the overall time. And so the idea is if you could map the electrical activity on the surface of the beating heart much more quickly than is currently possible with this by-hand, point-by-point probing, you could eliminate a lot of the time associated with the procedure, and you could more accurately identify the spatial extent of the aberrant tissue, so you eliminate the minimum possible tissue in the ablation or the resection process. And so we built a device to do that kind of mapping that involves an array of electrodes that interface to the cardiac tissue. And each one of those electrodes at each unit cell incorporates a multiplexing silicon transistor and an amplifier. The signals are weak, and you need to be able to do active matrix addressing of this array of sensors so you can reduce the number of wires that need to come out in order to address all of the sensor elements. So this particular device has about 2,000 transistors, these silicon nano ribbon transistors. It's all a sheet of plastic. And then the outputs occur through an asymmetric conductive film that then goes to an external data acquisition system for collecting the data. So let me show you the operation of this device in what's called an epicardial mode. So this is an open heart procedure. This is a pig, it's not a human, so may still be a little bit squeamish. I certainly am, although I watched this movie enough times to sort of desensitized to it. But anyway, so pig models turns out to be a good model for human hearts. About the same size for these Yorkshire pigs, which are about 90-pound animals. So this is the device. And so instead of the penetrating pins that I mentioned before, that brain interface, these devices don't involve any adhesives or any penetrating electrodes because the device itself is so floppy, the tissue is slightly wet. So you can almost imagine this being like a piece of saran wrap, a little thin plastic strip or sheet, just sticks there. And so you just laminate a very non-destructive mode for doing the interface. Of course, this is high-density silicon electronics. And this is the ACF film, comes out through a PCB board, and then there's a computer over here. So this thing mounts onto the heart as the diagnostic part of this cardiac ablation therapy, and then it can remain adhered as the heart is beating. So what I'm going to show you is this device operating in a purely diagnostic monitoring mode, where we can make these things multifunctional. So in this case, it's actually also pacing the heart in a sophisticated way. So you see the heart beat rate change dramatically. Somebody hit a computer key over here, and that changed the kind of pacing that was going on. We also have devices that can actually do the ablation. But what's published is only the diagnostic part of that process. So the thing is sitting on the heart is vigorously beating, but data is streaming out of the device at a very high rate, about 1 kilohertz per channel. So over the course of minutes, gigabytes of data is coming out, and it provides you a movie, essentially, of electrical potential on the surface of the beating heart that allows you to determine which tissue, region of the heart tissue is aberrant and which is behaving normally. So this is a movie of that kind of data collected from a healthy pig, so you're not going to see any aberrant tissue in this particular case. This is one spatial coordinate along one axis of the tape, and this is the other one. So this is position, and then each one of these pixels corresponds to the potential that's being recorded by that laminated, corresponding laminated electrode, rendered in a color scale in this way. And so this movie is actually dramatically slowed down compared to real time. This is an Ekg trace, so take a single pixel and plot the potential as a function of time. This is one beat sequence. This is polarization, repolarization event, another polarization, repolarization. So this is the beat cycle. And the pig's heart is beating between 60 and 80 times per minute in these kinds of systems. So this is slowed down. This dashed line gives you a sense of where we are in the beat cycle. You see a wave of depolarization move across the heart. That's the way normal cardiac tissue coordinates contraction. Then you see a repolarization event there, preparing the cardiac muscle for another beat cycle. You see that happen again. Wave of depolarization move in that direction, and then a repolarization event here. So in terms of cardiac electrophysiology and mapping, this is providing unprecedented spatial and temporal resolution for the purpose of a surgical procedure. So this is not meant to be a long-term implant. Something sits on the heart during preparation for the surgery, and then it's peeled off and thrown away.
So how do you deliver this to heart?
It's an open heart. Yeah.
Also
So the surgeon delivers it to the heart with forceps.
So on human you find low.
So okay, so this is perfect lead into the next two slides. So there are two ways to do this ablation therapy. One is in this epicardial mode, which is on the outer surface of the heart. That's open heart. The other, which is gaining popularity because it's a less invasive procedure, is endocardial. So in that case, the mapping and the ablation happens via a catheter that runs up into the interior surface of the heart through an artery or vein. And so what we're trying to do now is take the electronic functionality that's present in that tape and implement it on a catheter balloon so that the balloon is inserted in the heart, is inflated, and then that pushes the electronics to the interior surface of the heart. You can do the mapping and the ablation that way. So we haven't published that. That's the direction we're going, and that's what this slide is showing. So in this case, you need stretchable electronics at a pretty extreme level. So the dimensional change in going from this uninflated state on this otherwise conventional catheter to this state is about 400% strain. It's huge. So you really have to be careful about mechanics design and how you're doing this. In this case, the ACF film, of course, doesn't have to be stretchable, but it wraps the length of the catheter and then terminates on one end of the electronics.
So when you inflate a balloon, it's not like off, right?
No, just inflates like that kind of balloon and pushes itself against the interior wall.
So your circuits will open up like flat.
They're opening up. They're moving with the balloon. So in this case, these are the electrodes, and they're following the contour of the balloon, whether it's in the uninflated state or fully deployed like that.
So it's still the same shape.
Well, the shape of that balloon, which is, yeah, has actually symmetry, not a simple symmetry. So that's what we're working on now, is that we put electronics on balloons, catheter balloons. But we have all these different building blocks. You actually make a very sophisticated, multifunctional catheter to do more sophisticated things. So here we have temperature sensors, LEDs, individual electrodes for stimulating, ablating, and measuring. And so we think there are a lot of opportunities in this kind of advanced catheter-based device for stretchable electronics. So that's the direction that we're moving. This is Marv Schleppian, who's involved in a lot of our work. He's probably the world's leading cardiologist specializing in cardiac ablation therapy. So he will do about 300 ablation procedures per year. It's almost one a day. And we work closely with him because he understands what are the limitations of existing technologies. So this is an example of Marv and some other collaborators, also another collaborator down here, if you can consider it that. So let me shift gears then and talk about neural applications. And here we work with experts in epilepsy at UPenn. And the problem is kind of similar. It's a lot more challenging, but it's similar to the one that I just described to you in cardiac ablation therapy, in the sense that in cases of patients who are suffering from acute epilepsy, what is done is the skull is opened up. These kind of coarse electrode structures, so each one of those is an individual electrode, is wrapped on the surface of the brain. And then while the patient is awake, a seizure is stimulated, usually by administering certain drugs. And the output of measurements made at each of these different electrode sites is used to develop a map of electrical activity on the surface of the brain. And then you try to identify the region of the brain that's responsible for the seizure. And then you just cut it out. That's the way it works. And so you can imagine this kind of technology is quite primitive. It's purely passive electrodes that are large and sparse. So the kind of spatial resolution that you can obtain is extremely limited. And you would like to, as locally as possible, define what region of the brain needs to be removed so you remove the minimum amount, obviously. And so the goal is to take a circuit system kind of similar to the one that we had for the heart and adapt it for the brain. The brain's way harder, though. You might not think it's as hard because the brain's not moving around as much as the heart. But the electrical signals are a factor of 1,000 smaller, so your amplifiers, your electronics have to be much higher in quality. And also the surface is a lot more curved. So the heart has a fairly large radius of curvature. It's otherwise pretty smooth. Here you have deep folds and trenches and all kinds of shapes that the circuit needs to conform to if you want a high fidelity, low impedance coupling between the electrodes and the tissue. So that's pretty hard. What we're doing at the moment is making just sheets of electrodes and then doing unusual things. So this is an example of active electrode sheet, similar to what I showed you before, but designed in kind of a foldable format. You can wrap it around a soft insert like this. You can actually plunge it into the gap between the right and left hemispheres of the brain. This is the cat model in this case, to study the function of the brain. But this does not solve, so this is interesting, we're pursuing that, but it does not solve the challenge of conformal integration on the surface. So you can do interesting things with flexible electronics, but you really want highly contoured types of systems for on-surface measurement. And so here's the problem. So this is a 2-scale model of the human brain. So if you make a thin circuit sheet like the one we use for the heart, you put it on the surface of the brain. The capillary action associated with the wet surfaces of the circuit in the brain are not sufficient to drive wrapping. And you can see that here. I mean, the circuits are just too rigid to accommodate the sharp folds and surface of the brain. So that becomes a problem in mechanics that has a deceptively simple apparent solution, which is you can look at this system, you can ask, when will a sheet of plastic wrap a cylinder with a radius of curvature given by R? And that just happens when the bending energy is lower than the adhesion energy. That is to say, this thing will bend more easily than the energy associated with the contact of these two wet surfaces. So the bending energy is cubic, and the thickness depends on the radius of curvature. The adhesion energy just depends on gamma, and in this case, this length dimension. So gamma is a given for two wet surfaces. So if you want wrapping, you want the bending rigidity as small as possible. You could imagine going to a low modulus material, but you have limited headroom there. You can drive the thickness down. The problem with driving the thickness down to the extreme levels that I showed you before is that the circuit then becomes too floppy to manipulate. The surgeon needs to manipulate it and mount it on the brain. So if it's so floppy enough to wrap the brain, it's not self-supporting. It just falls on top of itself. So for a 50 micron thick sheet of plastic, which is a good ballpark number for something that's thick enough to be mechanically manipulated, you can really only wrap a surface with a radius curvature down to about 1.5 centimeters, even when it's wet. You can't do smaller than that. And so that brings me then to a slightly different idea that we're pursuing, and I'll describe that and then wrap up. I just have a few more slides here, which is for indwelling biointegrated devices. There may be certain situations where you would like the electronics not only to integrate in the way that I mentioned before, but also resorb, just simply disappear over time. So you can imagine if you've done an operation and you want to provide some kind of electronics for monitoring the wound healing, it might be advantageous for that electronic to simply disappear into the body after the wound is healed, so you don't have to go back in and fish it out. And so the question is, can you come up with fully resorbable materials for electronics that would allow that kind of system? And there are some materials that appear to be attractive. So we work with Tufts University on silk. Turns out to be a very nice platform for electronics, and silk is fully biocompatible, bioresorbable. If you make electronics, in this case, it's partly non-resorbable, silicon devices here, and partly resorbable silk. So you can actually insert this into an animal. Over a course of months, the silk disappears, just leaving small pieces of silicon. So the idea is you could perhaps design this system, it's not fully bioresorbable, to eliminate any kind of adverse reaction by choosing the mass loading, the total amount of non-resorbable material to be as small as possible. So that's a concept. I'll describe in 1 second how that relates to this neural monitoring application. But the silk itself starts from raw silkworm cocoons. There are ways to purify this material and cast thin films of it that are robust platforms for the kinds of electronics I've talked about up to this point. And so this is silicon devices on silk. So it's flexible, it's bioresorbable, but at the same time it's high performance. So you get sort of wafer-like performance characteristics out of devices that are mounted on silk. And it's fully water soluble. So you can take a piece of this silicon on silk electronics and you drop it into water. The silk will quickly dissolve. Dissolve at a rate determined by how you do the processing, and then that leaves you just with silicon devices that just swim away. So one interesting question that we're actually pursuing is, in the context of these systems, is what is the minimum lethal dose of transistors? How many transistors? What is the size and shape that the body can accommodate in these kind of resorbable systems? Now, in the context of the electronics, what the silk platform allows you to do is make a system that's sufficiently rigid that you can mount it on the brain. You can mechanically manipulate it. Once it's mounted on the brain, you simply flush the entire thing with warm saline solution, thereby dissolving the silk and allowing an otherwise too thin circuit system to wrap onto the brain. And so that's what we've done. So here's an example of a silicon-supported 2.5 micron thick electrode array. Here is the ultimate embodiment, which is that thickness but cut into a mesh geometry. So it's originally supported by silk. silk is washed away, thereby allowing this kind of conformal wrapping, in this case onto the tip of a glass pipette to illustrate what's possible. So you can do that on real animal models. This is a cat. So this is a conventional piece of flexible electronics. It does not wrap, as I mentioned before. This is an ultra-thin mesh of electrodes on silk after the silk has been washed away. So you can see this kind of conformal contact, even on this very, very curved, irregular surface of the tissue. And these are actually Ekg signals taken from the brain while the cat is exposed to a different series of images. And the green indicates a likely physiological response, and red is likely noise. So the much better contact yields a much higher fidelity monitoring. Okay, so that brings me to the end then. This is an area that we think is interesting. There are a lot of fundamental problems in materials, chemistry, and physics. I've mentioned a lot of these, understanding these interfaces and soft adhesion, microorganic mechanics. But in the context of a set of engineering outcomes in surgical devices, implantables, brain-computer interfaces that we think could have larger societal value. And so we're pursuing those aspects as well. So just in conclusion, this is a list of the senior collaborators. It's mechanics, theorists, chemists, neurologists, cardiologists, biomaterials types, as well as double E growers like Shu-Ling Lee, who works with us on gallium arsenide epi materials. And of course, all the work is done by a really outstanding collection of students and postdocs in the group. And we just acknowledge them. Thank you for your attention. Be happy to answer any questions.